I'm trying to decide whether or not I want to sneak in a small portion of what I had intended on covering on Monday today, just so that the amount of material that I'm giving you guys on Monday isn't ridiculously overwhelming. It's just a normal amount of overwhelming. So we'll see how I'm feeling after we cover the material for what we're supposed to do right now. So the first thing that I want to talk about is instantaneous power. In steady state sinusoidal circuits. And we are, as part of this talk, accidentally going to stumble into a relationship for average power as well. And then after we finish instantaneous power, I'm going to more formally describe how we could calculate the average power and all of that kind of good stuff. So let's say that I have a network. Going back to our good old black box network that we've used for every generic thing. And we are going to assume, once again, that this is a linear black box network. So only containing resistors, capacitors, and inductors, possibly current sources, voltage sources, but no nonlinear circuit elements like transistors or anything like that, which we've never used those in this class anyway. So nothing remotely new here, okay? And let's say that this network is sinusoidally excited such that we are able to measure, bless you, the voltage drop across the terminals of our network using an oscilloscope and the current flowing through our network also using an oscilloscope. So let's say that our voltage V of t is of the form Vm cosine omega t plus some phase angle theta v. And our current waveform I of t is also a sinusoidal function, Im cosine omega t plus some phase angle theta I. We can define the instantaneous power absorbed by our network and I'm going to put or supplied by our source because those are going to be the same quantity. Is given by the following expression. So before I hit you guys with some math, what do you think the power is going to be? I times V. Absolutely right. It is literally always I times V, okay? So our instantaneous power, P as a function of time, is simply going to be the product of our voltage waveform V of t multiplied by our current waveform I of t. Absolutely correct. So if I substitute in my expression for V of t, that's going to put a Vm cosine omega t plus theta v here, and an Im cosine omega t plus theta I over here. So I'm going to use a trig identity that I believe I've already shown you guys, but this will be my first time ever actually applying it. So just to remind you all, if I have the cosine of x times the cosine of y, This is the same thing as 1/2 the cosine of x minus y plus 1/2 the cosine of x plus y, where in this case, x is the entire angle omega t plus theta v, and y is the entire angle omega t plus theta I. So if I apply that trig identity, what I wind up getting is 1/2 the magnitude of the voltage times the magnitude of the current cosine. So let's look at things here really quickly. So omega t plus theta v minus omega t plus theta I, the omega t's are going to go away, and we're only going to have a difference of the phase angles. So that'll be simply theta v minus theta I. And then we have the second part of our trig identity. So we're going to have 1/2 times the magnitudes. And now we have to add those angles together. So we're going to have omega t plus theta v plus omega t plus theta I. And so that's going to look like cosine of twice omega t plus theta v plus theta I. So I have made a plot on Desmos that I want to show you guys so that we can kind of infer some things from this. So are we okay with me switching over to a different screen real quick? All right. There we go. So right now I have a voltage waveform in red. So I have an angular frequency of 2 pi radians per second and a phase angle of -62 degrees. And then I have a current waveform in blue, which has an angular frequency of 2 pi radians per second and a phase angle of -98 degrees. So this should look something like what you guys saw when you had your inductor network, right? Our voltage is leading our current. So if I were to plot the power, that's what that green curve is. So I'm going to get rid of something here just because it's a little busy. So I'm just going to turn off the current for right now. Okay. So we can make a couple of observations. Okay. So our power waveform, which is the one in green, is oscillating at twice the frequency of either our voltage waveform or our current waveform, right? So it's going through 2 cycles for every single cycle that our voltage or our current goes through. And that bears out in our mathematical expression because we can see that we have a twice omega t term here. Another interesting thing, and this actually might be more interesting in my opinion, is that our power waveform is not centered around the horizontal axis, right? Instead, it's raised up by some amount, okay? So the amount that it's raised up is what we would call a DC offset. And that DC portion is literally mathematically described by this guy right here. Okay. So 1/2 is a constant, Vm is a constant, Im is a constant, theta v minus theta I, that is a constant. So the cosine of a constant is also a constant. So all of these things put together just gives us some amount of DC power that is absorbed by our system, okay? Then over here on the right-hand side, we have our twice omega AC power term. So I'm going to put another plot on Desmos really quickly. So I'm going to call this P2. And this is just going to be the DC part, okay? So I'm going to have 1/2 times. So what's the magnitude of my voltage waveform here? 15. And then, excuse me, what's the magnitude of my current waveform? Just 2. And then I'm going to have minus, actually, let me throw another parentheses on here. Minus 62 minus negative 98. So that's going to look like plus 98. And then I'm going to pi over 180, exactly right. Just because I'm using Desmos's default setting for an angle in radians. Okay. So this purple line represents that DC portion. I've literally just plugged in the values from our current and voltage waveform and plotted it here. What is that purple line? It is a straight line because it's a constant, absolutely. But notice what it is in relationship to the green line. So exactly half of the time, our green curve is above that line, and exactly half of the time, it's below it, right? Because we have a simple sinusoidal oscillation. So what would you call that? So I would call it the average value, because exactly half of the time it's above and exactly half of the time it's below, and it's symmetrical about that line. So the DC portion of our instantaneous power is actually just our average power. Okay. So I'm going to write that down over here. Oops. Okay. Okay. We're going to more formally derive a relationship for average power in a few minutes, and we are actually going to wind up getting the exact same thing that we observed just by looking at the graph and trying to understand what's going on. Okay. So we have this generic expression. I'm going to put a box around it. It is important. You guys are going to be using it for the next couple of class meetings, and you'll have something about it on your test for sure. Speaking of your exam, there is an equation sheet for the exam that I have prepared. Okay. So back in the day, we just had this, what I felt was a crappy equation sheet, but I was too lazy to fix it. And so this summer, I actually took the time to write out a good equation sheet and all that kind of good stuff, and I will have it uploaded to Canvas later today, especially if one of you guys shoots me an email to remind me to do it. It will actually be later today and not just sometime this weekend when I remember it. But anyway, I would encourage you when you're working your homework assignments over the next couple of class meetings and all of that kind of stuff to have that equation sheet in front of you so that you're used to using it, so that when it comes time for the test, it's not new to you. Okay. But anyway, so this is definitely going to be one of those equations that's on that equation sheet, because this is big and ugly and gross. And while I can remember it and know how to derive it, I can't really expect that of all of you guys, you know, because you haven't done this for 7 years straight. Okay. So this expression that we have derived is a generic expression because we don't know what's in our linear black box network. It could be literally anything. So we can always fall back on this expression. However, it requires us to know both the magnitude of the current and the phase angle of the current, the magnitude of the voltage, and the phase angle of the voltage. So effectively, a couple of things that we can unpack there, right? First, since we're only interested in magnitudes and phase angles, even though this is a time domain quantity, our analysis is still going to be in the frequency domain. We're just going to take the parts of our phasors that we need and plug them into this equation, okay? So you should never, ever get imaginary numbers when you're using this thing. If you are, you're doing it wrong. We literally just take the magnitude, take the phase angles, and plug them in where the equation tells us to do so, okay? One of the reasons why I don't particularly like this equation in some situations is because it requires me to know both the phasor voltage and the phasor current across my element or network of interest. So what we're going to spend the next few minutes doing is breaking this down for if we just have specific components, because we can actually simplify this relationship pretty considerably, okay? So let's first consider when we have a resistor. Okay. So for a resistor, we know a few things, okay? And these are going back to our frequency domain relationships that I introduced, I think early last week, before we got into our steady state sinusoidal analysis, or maybe it was the week before. But we should remember that the voltage drop across our resistor is simply the magnitude of the current times the resistance value. And we should also remember that the phase angle of the voltage is the same as the phase angle of the current. This will always be true for resistors. We derived these relationships a week or so ago. Okay. So I can use these relationships to express my power equation only in terms of voltage or only in terms of current, meaning I don't need as much information to get the power that I'm interested in, okay? So when we have a resistor, this is a potential shortcut, okay? So let's say PR of T will be 1/2, okay? So let's put everything in terms of voltage first, okay? So my VM is going to stay VM. Well, how would I express the magnitude of my current in times of VM? Just divide by both sides by R, right? So IM being replaced by VM over R gives me VM squared over R, okay? Just simple substitution there, all right? Now, I have this cosine theta V minus theta I bit. But I know that for a resistor, theta V and theta I are literally the same thing. So what's the cosine of 0? 1. So I don't actually need that cosine bit at all. So I'm just going to put 1 plus, and now I am out to the second part where I have that 1/2 VM IM, which is still just 1/2 VM squared over R in terms of only voltage quantities. So I'll have cosine twice omega t. And now theta v plus theta I could be written as simply twice theta v. So that's my instantaneous power in terms of only voltage. Okay. So for what it's worth, well, actually, let's go a little bit further here. So what should we expect our average power to be based on this relationship, with the understanding that the average power is just the DC part, 1/2 VM squared over R. So it's almost the same thing as our DC relationship, except that there's a pesky factor of 1/2 in front because of that trig identity that we're using. Okay. In terms of current, this is going to look like 1/2 IM squared times R, right? We leave the IM alone, we substitute IM times R for VM, multiply those guys together, we get IM squared times R. Cosine of 0 is still 1, so this is now just going to look like 1 plus cosine twice omega t plus twice theta I. And what would our average power be only in terms of current? 1/2 IM squared times R. So once again, extremely similar to our DC relationship, except that we've got that pesky factor of 1/2 in there, messing things up. Okay, so I want to pop back over to Desmos real quick and show you guys what this would look like for a resistor. And so all I'm going to do is change this thing right here from -98 to also be -62. And then that's just going to make this guy right here 0. I'm going to turn off the red so that all we see is our average power and our instantaneous power for a resistor. So we can make a couple of observations here, I think, okay? Notice that the instantaneous power never dips below the horizontal axis. What does that mean? So this is a graph of the power absorbed by a resistor. It never supplies, which we already knew from the third day of class, okay? So our AC understanding of power absorbed by a resistor still matches everything that we knew from our previous lectures. A resistor literally will never, ever, ever supply power. It will dip down to zero, and that's as low as it can possibly go. That will never be a negative quantity, okay? So the average power is always just 1/2 of the maximum amount of power, okay? All right. So now let's look at relationships for an inductor. So for an inductor, we know that the magnitude of our voltage, Vm, should be omega L times the magnitude of our current. And we also know that theta V will be equal to theta I plus 90 degrees. So the current is always lagging the voltage by exactly 90 degrees. You guys probably found something close to that relationship in our lab on Wednesday. You wouldn't get exactly 90 degrees because we don't have an ideal resistance, or excuse me, an ideal inductance. So the resistance of the coil itself, the wire in the coil itself, is going to push that a little bit away from 90, but it shouldn't have been huge. So if you did everything correctly, should have come out to be somewhere in the ballpark of 80 to 85 degrees. All right, so for our inductor, expressed only in terms of voltage, what we're going to wind up having is 1/2 Vm squared over omega L. So in case you haven't noticed just yet, this is literally just Vm squared divided by the magnitude of the impedance that we're looking at. So when it was a resistor, it was just the resistor value. For an inductor, it's omega L. For a capacitor, in a couple of moments, it'll be 1 over omega C. It's just the magnitude of the impedance. Okay. Now we are, gonna have that cosine X minus cosine Y term, okay? So I'm gonna write this down here in red, and I'm gonna wind up erasing it in a minute. I just want to show you guys what's going on. So we're gonna have cosine of theta V minus theta I. Well, theta I is just theta V minus 90 degrees. So this is the same thing as cosine of positive 90 degrees, just by doing a simple substitution, okay? What's the cosine of 90 degrees? 0, okay? So what does that mean, jumping a little bit ahead, for our average power? The average power absorbed by an inductor is 0. Okay. So now over here, we're going to have cosine twice omega t. When I add those two angles together, I'm going to get twice theta v minus 90 degrees. Okay. In terms of current, my instantaneous power absorbed by my inductor is going to look like 1/2 Im squared times omega L cosine twice omega t plus twice theta I plus 90 degrees. And just as easily we can see from this relationship that since there is no DC term, the average power is 0. So I'm going to plot this even though we all should know what a cosine function effectively looks like, just because I want to make a couple of notes here as well. So I need my current to lag my voltage by 90 degrees. So what's 62 minus 90? Is that 152? Or negative 62 minus 90, I think would be negative 152. And then we know that our average power term should literally just be 0. So this is what it would look like. Okay. Exactly half of the time, our inductor is absorbing energy or absorbing power, and exactly half of the time, our inductor is supplying energy or supplying power, right? So when we go back to, I think I originally had this as like negative 98 or something like that. So if we looked at that generic network originally, where we said that it looked kind of inductive, like when we had a resistor and an inductor in series, notice that our instantaneous power, most of the time, it's positive, but some of the time it's negative. And that some of the time that it's negative is when the inductor is supplying power into the system. So our temporary energy storage elements, like capacitors and inductors, actually pump power back towards the source, okay? This is something that we're going to talk about when we're talking about complex power in a couple of days, and about inefficiencies and things like that in the system, because this represents effectively power that's being generated and then being sent back to the source. All the inductor or a capacitor can do is absorb it and then give it right back, okay? Sounds like a waste, but without that, our electricity grid would not work. Okay, so anyway, we'll talk about that more in detail in a couple of days. Okay, so lastly here, we have our relationships for a capacitor. So in a capacitor, we know that the magnitude of our current is omega C times the magnitude of our voltage. And we know that theta I is equal to theta V plus 90 degrees. So our current is always leading our voltage by exactly 90 degrees in this case. So our instantaneous power relationship is going to look like 1/2 Vm squared times omega C, because dividing by 1 over omega C is the same thing as multiplying by omega C. Cosine theta V minus theta I is actually going to look like cosine of negative 90 degrees in this case. Cosine of negative 90 is still just 0, so our average power is 0. And then we're going to have cosine twice omega t plus twice theta V plus 90 degrees to finish up our voltage relationship. And then lastly, our current relationship. We have 1/2, Im squared over omega C cosine twice omega t plus twice theta I minus 90 degrees. And once again, our average power is 0. And the graph for the instantaneous power absorbed by a capacitor is going to look effectively the exact same thing as it did with the inductor. It's just going to be shifted to the left or right because it's just different phase angles. All right, so before we move on from this, you're going to have in-class assignment problems to work and homework assignment problems to work where you're applying this equation. The most common mistake that I see, just to clarify things here, and this is true for any of these individual parts, so I'm just going to talk about it down here. This bit right here is an angle in radians, right? So omega times some time in seconds, so radians per second, times seconds gives us an angle in radians. We all okay with that dimensional analysis. This phase angle over here is an angle in degrees. Our calculator wants one or the other, right? So you need to make sure when you're doing these calculations that you either multiply your angular frequency by a factor of 180 over pi to put everything in degrees, or multiply your phase angle by a factor of pi over 180 to put everything in radians, and just use whichever one is appropriate for what your default setting of your calculator is. My calculator is always in degree mode, so I usually do twice omega t times 180 over pi. So I just want to make you aware of that, that if you forget that angle conversion, you are not going to get the correct answer in the in-class assignments, the homeworks, the exam, all of that kind of stuff. So I'm telling you explicitly, don't forget to do the angle conversion, or it's going to bite you in the ass real hard. You can do everything else right, and that will give you a wrong enough answer to where you'll miss points for, whatever. Okay. Let's talk about average power more formally. So before we talk about average power, I want us to understand how we would compute the average value of any periodic function. Okay. So let's say that x of t is a periodic function with period capital T, right? So this could be a sinusoidal function that repeats itself every so often. It could be a non-sinusoidal function. It just matters that it is periodic, meaning that it repeats itself at regular intervals, and that regular interval is the period T. We all okay with that? All right, so the average value of x of t is given by the following relationship. Okay. So I'm going to call this x average is 1 over the period multiplied by the integral over 1 period of our periodic function. This is hopefully something that you guys learned way back in Calc 2, I think, because you have to use an integral to do it. But effectively, you integrate the function over 1 period, and then you divide by the length of the period to get the average value. So intuitively, it makes sense to me, but I've had to do this math for a long time. So, for what it's worth, I think you guys actually had to do this way back on homework set number 1. You may not remember it, though. But anyway, so this is the average value of a periodic function x of t. Well, we've seen that our power waveform is a periodic function. So let's see what happens if we plug that into this equation, okay? So our average power, P average, would be 1 over our period, and we'll sort this out in a moment if we need to, times the integral over 1 period of 1/2 times the magnitude of our voltage times the magnitude of our current, cosine theta v minus theta I, plus 1/2 magnitude of the voltage, magnitude of the current, cosine twice omega t, plus theta v, plus theta I. All of this integration is occurring with respect to time. So I'm just using the generic relationship because if it works for this, it'll work for literally everything. So I can break this big gross integral into two smaller, slightly less gross integrals. So actually one of them is really less gross and the other one we'll talk about here. So I would have 1 over time, or 1 over period, excuse me, times the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt plus the integral from 0 to t of 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. Close those braces. So does anybody have a problem with me splitting that integral up into two integrals? Since our original integral was just the sum of two functions, I'm just integrating both of those functions and adding the results together. And because integration is a linear operation, that's perfectly okay. So let's look at that second integral first, okay? And we are not going to evaluate it per se. We're simply going to look at it and see if we can figure out what's going on. So this is a cosine function oscillating at some particular angular frequency twice omega. So I'm going to attempt to draw that part. So to make my life easier, I'm going to say that theta v plus theta I added together is just going to be 0, so that I can draw it less shittily. But if it weren't 0, we would just be sliding this graph either to the left or the right. Wouldn't change the heights or anything like that. So looking at this representative graph, this guy right here represents the amount of time it takes for this signal to repeat itself, right? That is 1 period. So it started at its maximum value and it's ending at its maximum value. Okay? If I were to take the integral of this waveform over 1 period, what would I get? 0. Because exactly half of the time it's above the x-axis and exactly half of the time it's below the x-axis. So those areas under the curve cancel each other out, right? So effectively, this area plus this area is exactly canceled out by that area underneath. So this whole integral is just 0. Okay. That will be true whenever we integrate a sinusoid over any integer number of periods. I'm saying that specifically because we're going to do this again, and I'm going to say it's 0 because we've already talked about this. So I'm just making it really clear. If we integrated over any integer number of periods, it's always going to come out to be 0 because the positive peaks will always be canceled out by the negative peaks. So all we have left then is this stuff over here on the left. Literally all of that is a constant. We've already discussed it before. So I can pull all of that outside of the integration. So I would be left with 1/2 Vm Im cosine theta v minus theta I times a factor of 1 over t multiplied by the integral from 0 to t of dt. What's the integral from 0 to t of dt? Capital T. Capital T divided by capital T is just 1. So this business right here just comes out to be 1. And we can see that based on our mathematical definition of average value, we get 1/2 Vm Im cosine theta V minus theta I, which is exactly what we got when we just observed what was going on with our graph. So two different ways to look at average power, both giving us the exact same results. This methodology here, where we're using, taking the integral of our periodic function over one period and then dividing it by the length, will work for any signal, or any periodic signal, not just sinusoids. Okay. I think I have enough time to talk about effective values without me speaking for like a ridiculous amount of time today. So we're going to move one topic from what would have normally been Monday's lecture today, just so that Monday's lecture isn't as horrifying. And this is actually rather related to what we just talked about anyway. So effective values of periodic waveforms, or signals, or whatever you want to call it. So whether we realize it or not, we actually have probably been using effective values for some signals in our everyday life, okay? So to explain what I mean by that very specifically, I want us to consider a receptacle that we see all in our homes and all of that kind of good stuff, okay? So bear with my inability to draw things. So we have our receptacle. Let me look and see. So I have like a long socket here, and then a shorter socket here, and then kind of a circular-ish, semicircular socket there. So that is my terrible rendition of a receptacle, or what you guys are probably more familiar with, an outlet that we might find in our homes. For what it's worth, the outlet thing that I have drawn here is what's called a NEMA 15R receptacle. This guy right here is a 20R receptacle, and I can tell that because it has a little P thing on the side of the deal. That just means that that one's rated for 20 amps, this one's rated for 15 amps, and if you give a shit about the NEC code, all of it is in there. Most of you probably won't, but for those of us who are working on our professional engineering licensure in electrical engineering, that kind of detail matters. Anyway, so we have a receptacle. This bottommost pin is typically connected to a green wire inside of the walls of this building. And this is our ground wire. And it likely connects up somewhere inside of our load center, or what you guys more commonly call a breaker box. And then that connects to a ground pin outside your home that is literally a metal stake buried in the ground to give the potential energy of the earth as the reference for all of the voltages in your home, if your house is grounded correctly. I'm going to do this in, yeah, actually this will be fine, yeah. This one is usually in black. So this is what's called our neutral wire. And it serves as the negative polarity terminal of the voltage that's being provided by our outlet. On the right-hand side, this wire in our homes is actually usually white, but white's not going to show up, so I'm going to draw it as a red, okay? And so this is what we would commonly call the hot wire. And this serves as a positive polarity reference for the positive polarity terminal for anything that we plug into our outlets. So my question to you guys is, what's the voltage provided by one of these outlets in our homes? 120. Okay. So that is the answer that I'm expecting. So I'm going to write 120 volts down here. And then I'm going to tell you that you're both right and wrong. So let's talk about why you're both right and wrong. Okay. Is the voltage that's coming out of that outlet a DC quantity? No. So how did you just describe it as if it were a DC quantity? Because 120 volts is a constant. And there is definitely not 120 volts as a constant value coming out of that thing, okay? Instead, the voltage as a function of time between those two terminals, V of t, is, make sure I do the math right here. I'm going to put approximately because it does change slightly, but it should be somewhere very close to 169.706 cosine 120 pi t plus whatever phase angle is introduced by at the particular time that we start measuring. Okay. So how the hell do we go from 169.706 cosine 120 pi t plus a phase angle to 120 volts? Okay, so that's the question that we're going to answer here really quickly. So this 120 volts is correct if we are considering this to be what's called an RMS voltage. Okay? So RMS stands for root mean squared. And those are literally the mathematical steps that we are going to apply to that time domain voltage to get that 120 volts, okay? So let me now explain what an effective value actually is, okay? So an effective value for a voltage or current periodic waveform is a DC equivalent voltage or current that delivers the same amount of average power as the periodic waveform. Meaning that if we hooked, let's say, a light bulb up to this receptacle, and we hooked a light bulb up to a 120 volt DC source, the exact same amount of average power would be absorbed in both of those systems, okay? So an effective value is just a DC representation of an AC quantity that absorbs the same amount of average power, because it's absorbing the same amount of average power, but it doesn't contain nearly as much information, so it's not such a pain in the ass to use effectively, is why effective values are actually used. And we're going to find out here in a couple of moments that they're going to change our power relationship slightly, and they're going to get rid of those pesky 1/2 signs that we kept seeing crop up for steady state sinusoidal systems. Okay, so let's now figure out a mathematical relationship for calculating effective values. And I've already talked about this. It is the root mean square process. But we can figure this out fairly quickly by looking at a couple of things. Right. So let's say that I have a resistor. Okay. the average power absorbed by my resistor could be expressed as 1 over T times the integral from 0 to T of the voltage drop across my resistor squared divided by my resistor value itself. Where that V squared over R is literally just the instantaneous power absorbed by a resistor. So does anybody have any questions, comments, or concerns about where that particular relationship came from? Hopefully we're all familiar with V squared over R for power for a resistor. Okay. Very similarly, let me put it down here. I could say that the average power absorbed by a resistor is the current flowing through the resistor squared times the resistor value itself, right? Just using I squared times R as our instantaneous power when we know the current. Okay. So now let's talk about what happens in a DC circuit. So in a DC circuit, the average value is the same thing as the instantaneous value because it's just a constant, right? So it can never not be the average power. So in terms of voltage, what's the average power absorbed by a resistor in a DC circuit? V squared over R. So I'm going to call our voltage here the effective voltage because that's what we're looking for. And similarly, down here, we're going to have P average is equal to I effective squared over R. So if I put these two things equal to each other, what I wind up having is 1 over T times, actually, let me put the V effective thing on the left-hand side. V effective squared over R is equal to 1 over T times the integral from 0 to T of our periodic voltage waveform squared divided by the resistance value, and then I'm integrating with respect to time. So I can notice very easily that there is a factor of 1 over, yes? Oh, it should be times R. Thank you for that. Yep, I just had a total goof. You are 100% correct that I made a mistake. Thank you for pointing that out. All right, so going back to what I was saying a moment ago, there is a common factor of 1 over R on both sides of the equal sign. So I can get rid of that. And so if I'm trying to solve for V effective, I simply need to just take the square root of both sides now. So if I take the square root of that guy, that's going to get rid of that. And it's going to put a square root sign over here. And boom, I have derived my relationship for my effective value. If we look at our current relationships, similar thing, right? We're going to have I effective squared times R is equal to 1 over T times the integral from 0 to T of I squared R dt. There is a common factor of R on both sides that I can get rid of. If I take the square root of both sides, I'm left with this. So the equation is effectively identical. If we have a signal, a periodic signal that we want to take the effective value of, we square it, we integrate it, we divide it by the period, and then we take the square root of the whole thing. So RMS, root mean squared. We are taking the root, square root, of the arithmetic mean, that's just a fancy word for average, of the square of our signal of interest. It's literally what we're doing. So whenever we get voltages here, we're going to give them units of volts RMS so that we know that we're dealing with an RMS or effective value. And whenever we apply this equation to currents, we'll have units of amps RMS to let us know that we're dealing with an effective value once again. So let's put this equation into practice for a couple of common signals that we see in electrical engineering, okay? So let's start with a square wave. So here's time. Here is voltage as a function of time, but this math would work exactly the same if it were a current. And let's say that I have a signal like so. So it's high for some fixed amount of time. Let me draw this a little bit better. I was thinking about adding in duty cycle, and then I decided not to because I don't want to piss you guys off. So let's just say that we have a square wave repeating like this, where this point in time right here is the period. And so this point in time right here is half of the period. This value of the voltage is some peak value V naught. And this negative peak value of the voltage is negative V naught. So effectively, this signal is symmetric about the horizontal axis. It's positive for some fixed amount of time, and then it switches to negative for that same fixed amount of time, and it just repeats that over and over and over again. Exactly like the square wave that you guys used when you were testing to figure out what the capacitor value was on that RC circuit that we dealt with a few weeks back, okay? So how would I describe this function mathematically? I personally would use a piecewise function, right? And if we're only trying to describe it over one interval, right, or over one period, because that's all that we're interested in when we're calculating effective values, I would have that it's some value for 0 less than t less than capital T over 2, and then it's some other value for capital T over 2 is less than t is less than capital T, right? Those are the two intervals that define my piecewise function. What are my voltage values? V naught and negative V naught. Nothing particularly difficult about that, I hope. And so if we want to define the effective value for this waveform, let's do that over here. So we would have the square root of 1 over capital T times the integral. So I'm going to integrate over one period. So because I have a piecewise function, I'm splitting my integral up into its two different intervals. Actually, let me put the generic equation first so I don't. So this is our generic equation. And then I'm going to apply this to our particular signal. So 1 over t, integral from 0 to capital T over 2 of V naught quantity squared plus the integral from capital T over 2 to capital T of negative V naught quantity squared dt. Close my brace, extend the square root sign over the whole thing. So before we get into the math here, does anybody have any questions about how I got to that second step? So when I have a piecewise function, I'm just going to integrate over each of the individual intervals that make up the piecewise function. And I'm literally just substituting my voltage value in whenever I have my V squared. And I'm remembering to square it because if I don't do that, I'm not getting the RMS value. Okay, so this should be fairly straightforward. So V naught is a constant and V naught squared is a constant. So I'm just going to have V naught squared times the integral from 0 to t over 2 of dt. Negative V naught quantity squared is also just V naught squared. Integral from capital T over 2 to capital T of dt, like so. And then that's going to look like the square root of 1 over t times V naught squared. I'm just pulling that out. So the integral from 0 to capital T over 2 of dt is literally just t over 2 minus 0. And then the integral from t over 2 to capital T of dt is just capital T minus capital T over 2. Like so. So I have a positive capital T over 2 minus capital T over 2. So those guys cancel each other out. So what's left inside those brackets is just capital T minus 0. So that gives me effectively capital T over capital T times V naught squared. Sorry, that squared looks like shit. Is just V naught. So for a square wave with a 50% duty cycle, meaning that exactly half of the time it's low and half of the time it's high, it's literally delivering the exact same amount of power as just a constant DC of its maximum. And you guys literally worked an example showing that on your first homework set in this class. Let's look at a different one. So this isn't something that we've used in this class yet, but it is something that is used fairly regularly in electrical engineering. And this is what's called a triangular wave or a sawtooth wave. So we have some voltage waveform V of t like so. And our signal is simply a series of triangular pulses like so, repeating forever. Let's call this value capital T and the peak value of our triangular pulse V naught. How would we describe this voltage as a function of time over just one period? Yeah, so y equals mx plus b. So what's m? V naught over capital T times lowercase t. Our y-intercept in this case is just 0. So that's it. So if we want the effective value of this guy, our generic equation, just to remind you all, and now I'm going to plug in stuff for our system. So our period is still literally just 1 over t. Our integral will occur from 0 to t. Our voltage squared is going to be V naught over capital T times lowercase t quantity squared dt. So before I get into the math here, are we all okay with what I've done? All right, so what I'm going to do is I'm going to pull out that V naught over T quantity squared. So that means I'm going to have a V naught squared over t squared. And now I'm simply integrating from 0 to t squared dt. Are we okay with that? Just pulled my constants outside from underneath or outside of my integration. What's the integral of t squared? 1/3 t cubed, right? So just combining things here really quickly, I would have v naught squared over capital T cubed, and then I'm going to have 1/3 of t cubed evaluated at capital T and 0. So this is going to look like v naught squared over t cubed times a factor of 1/3 times t cubed minus 0. The t cubed cancels the t cubed, and we are left with simply v naught over the square root of 3 as our effective value. So whatever the peak value of our triangular wave is, divide that by √3, and we have our effective value. Does not matter how quickly, so like at what frequency our square wave, or excuse me, our triangular wave goes. Doesn't matter if it, completes it in a millisecond or 3 minutes. It's literally just peak value over √3, regardless of how quickly it cycles. Okay. All right. So one last thing. Let's do a sinusoid, because that's what we're actually interested in. Okay. So let's say that v of t is Vm cosine omega t plus theta v. A generic sinusoid having any angular frequency, any phase angle. Okay. The effective value is going to be the square root of 1 over t times the integral from 0 to capital T of, I'm using that trig identity from before, where I'm just going to subtract the angles and then add the angles, the one that I used on the first page. So this is going to look like 1/2 Vm squared plus 1/2 Vm squared cosine twice omega t dt. Where this guy underneath, let me just put it here so that you can all catch what I'm throwing. This is just v of t squared. Okay. Now, the period here, t, is the period of the voltage signal, not the voltage squared. Okay. So what is the period for that signal? 2 pi over omega. We discussed that for what it's worth when we did our review of sinusoidal signals. I know this is boring, I'm sorry, but we're almost done. It's okay. It's early, and this is just a bunch of math. Do not feel bad for yawning. I would too. So we're going to plug in this t into our mathematical expression here. Okay. So I'm just doing it down here. So 1 over capital T is going to look like omega over 2 pi. And now we're integrating from 0 to 2 pi over omega. Now we could split this integral up into 2 parts, but I just want us to look at things really quickly, okay? When we integrate that AC portion, that is an integral over exactly 2 periods. What should that integral go to? 0. So just to be real clear, you're all catching what I'm throwing. Put an arrow, draw a little picture here. Bless you. So if I have this thing where this amount of distance is capital T, I have this amount of area is canceled by this amount of area. This area is canceled by this one. This one is canceled by this one. This one is canceled by this one. And obviously the integral over 2 periods is just 0. So all we're left with is that 1/2 Vm squared dt, which is literally just a constant. So we would have 1/2 Vm squared times omega over 2 pi times the integral from 0 to 2 pi over omega of dt, where this guy and this guy multiplied together is literally just 1. So we get our magnitude over the square root of 2. Now, I swear to God, I'm almost done ranting at you guys. Like I've got like 40 seconds left, okay? This result is independent of frequency and it is independent of phase angle. So it doesn't matter if we're here in the United States where our electrical distribution system is set up to oscillate at 60 hertz or 120 pi radians per second. It does not matter if we're in Europe where everything works at 100 pi radians per second. It does not matter if we are in Japan where half of the country is at 60 hertz and half of the country is at 50 hertz, depending on which country occupied it after World War II. Does not matter. Anywhere we go, a sinusoidal signal, its effective value is just Vm over the square root of 2. So if we look at our average power relationship that we just developed, P average is 1/2 Vm Im cosine theta V minus theta I. I could split that 1/2 as Vm over root 2 times Im over root 2 cosine theta V minus theta I, or simply V effective, I effective, cosine theta V minus theta I, meaning our average power can just be calculated using effective values. This relationship right here is where we are going to jump off from to figure out everything having to do with complex power. It all stems from that one thing. Now I am done ranting. I apologize for how long that took.